Welcome back to part 5 on solving trigonometric equations. Let's look at 4 sine x times cosine x equals the square root of 3. We're encouraged to use double angle identities here. And so I'm going to think about that as I break up the left side of this equation. I'm going to go with 2 times 2 sine x times cosine x, and that's equal to the square root of 3. And then I'm going to divide both sides of the equation by 2, and that should give me something that I'm familiar with. I have 2 sine x times cosine x equals the square root of 3 over 2. From here I can replace 2 sine x cosine x with sine of 2x. There's my double angle identity coming into play, and now we have square root of 3 over 2 equals sine of 2x. Now I'm going to impose a sine inverse on both sides to isolate the 2x, the double angle. So now I have sine inverse of sine of 2x equals sine inverse of root 3 over 2. And if I look at a unit circle, I happen to know that root 3 over 2 occurs at pi over 3 and also at 2 pi over 3. So I have 2x is equal to pi over 3, and also 2x is equal to 2 pi over 3. Now each one of these answers occur every full rotation around the circle, or for every period of sine of 2x, assuming that sine continues on. So every period of sine, this will happen again. So we assume that that's every 2 pi, which means I'm going to add 2 pi k to both of these solutions at this point. And then I'm going to solve for theta, or for x in this case, the angle. So I'm going to divide everything, or multiply by a half, which is equivalent, by 2. And my solutions are x is equal to pi over 6 plus pi k, and also x is equal to pi over 3 plus pi k. It's important to point out that for when you're solving these angles, when they're double, triple angles, whatever they happen to be, you need to keep in mind the period for the trig function first and foremost, because the period for sine is 2 pi, and the period for tangent is just pi. And so when you're looking at those repetitions, you have to keep that in mind. When I went ahead and solved for the angle x in this case, I had to start with 2 pi k, assuming that this continues on where k is an element of the integers. And then I divided by 2 on the angle to get the actual value for the angle. In this example, we have tangent x plus root 3 equals secant of x. It's going to be helpful to think of the actual equations that are being set equal to each other in this example before we do much else. So first of all, let's recall what secant is. Secant is 1 over cosine, or the reciprocal of cosine. So let's sketch cosine first. There's one period of cosine, so now I'm just going to dot the next little bit here in both directions. And then I'm going to put vertical asymptotes wherever the cosine crosses the x-axis, because that is where secant is undefined. And the pattern continues. Now for one period of cosine, we have secant as these U shapes that are tending toward the vertical asymptotes. So the period on which one interval of secant exists is from 0 to 2 pi. And I'll go ahead and graph 0 and 2 pi so we can kind of have a reference point for the next step. The next step is to identify where tangent exists. Now remember, cosine crosses the x-axis at pi over 2 and 3 pi over 2. And pi is here in the middle, which is convenient because tangent exists from on a period of pi in length, and on the interval from negative pi over 2 to pi over 2. So it kind of looks something like this. But recall that this has been shifted up, tangent of x has been shifted up root 3. So it's no longer going to cross at 0, 0. It's going to be that same shape, but it's going to be crossing up here somewhere. And so if you wanted to, you could graph y equals tangent of x in your calculator, and y sub 2 equal tangent of x plus root 3, and y sub 2 equals secant of x, which is equivalent to 1 over cosine of x. And you could compare where these two intersect. Note that it's going to be in the negative angle region because the intersection happens to the left of 0. And then for every additional period of the secant function, which happens every 2 pi, you're going to have another one of these intersections with tangent of x plus root 3. Now, once you know that, it's going to be a little easier to solve this thing. It says to square both sides as the hint and then use identities. So we'll go ahead and do that. We have tangent of x plus root 3 equals secant of x, and then we'll square both sides, and we'll get tangent squared x plus 2 root 3 tangent of x plus 3 equals secant squared x. Now remember, this is a Pythagorean identity, and that secant squared x equals tangent squared x plus 1. So I'm going to replace that with tangent squared x plus 1 on the right, and tangent squared x plus 2 root 3 tangent of x plus 3 on the left. Now I'm going to cross out the tangent squared x's because there's one on each side. So I'm subtracting them out. And then I have 2 root 3 tangent of x. I'm going to go ahead and subtract the 3's on both sides. So I'll get negative 2 on the right. Then I'm going to divide both sides by the 2 root 3, and my tangent of x has now been isolated, and it's equal to negative 1 over root 3, which is equal to negative root 3 over 3. That means tangent of x now needs to be isolated for just the angle, and I can do that by taking the tangent inverse of both sides, and I have tan inverse of negative root 3 over 3 is the angle I'm looking for. Pi over 6, and it's negative because it's in the fourth quadrant. Again, that's related to my drawing over here of why it's this number. But then the question is, when will that repeat again? And if I were to continue my little curve off here, I know that my secant function has period 2 pi. So I know that this angle will have an intersection with secant of x every 2 pi k.